today we will start discussing on digital logic part 1, but before that I want to revisit a quick summary of the previous 2 lectures. Mainly the previous 2 lectures I gave an introduction of digital system design. What do we mean by the digital design? So, starting from the design idea that if I want the digital ICs, so first it should be the behavioral description, means that given the problem, how I describe the behavior of my problem. Normally nowadays the CAD tools are used for that purposes, mainly for the size and the complexity of the circuits. And this is a very small snapshots how the today's hardware description languages Verilog or VHDL they look like. So, this is we can tell that behavioral description by hardware description languages. Then the CAD tool will partition the whole system, and some modules it will be generated from there. That means the original system is partitioned into some modules, and we call the second phase is modular description. So, just some block diagram level it was being shown. So, how what do we mean by module? We have described that thing. Or what do we mean by modular design? What are the different type of approaches we have taken, say that top down design approach or bottom up design approach. So, we have discussed that part. Then the logic design synthesis, the gates and flip flops, the third phase. So, once the modules are defined, then each module again it is partitioned into some subsystems or sub modules, and this is nothing but a set of gates, flip flops. So, the third phase is given by that. So, what we can tell that starting from the problem or the design idea, when we reach the logic design steps, this we are calling the logic design phases. And next each gate are again represented by some transistors. That means what we can tell, now the gate is a smaller subsystem and again it is partitioned into smaller systems, that means the transistors. So, the transistor level module, and this is shown in the fourth step. And next and the last we can tell that actual digital ICs, that means on a piece of silicon that actual transistors are fabricated and we get our final IC that is shown in the last step. So, starting from that transistor description or synthesis of the system using transistors and to get a digital IC, we call this is my physical design, that actual physical electronic equipments, whether it is a transistor or whether it is a piece of silicon, that we have achieved. So, mainly this is my specs of our this digital system design class. Today we will start the digital logic, that mainly the topics we will cover, the basics of digital computer systems, then understanding the decimal numbers. Mainly the number system we will read in this class. So, binary, octal, hexadecimal and different coded binary coded numbers, say BCD numbers, that we will read, and then the conversion between different number systems. So, today we will start discussing on the number systems first. So, first the digital, again the digital computer systems, that it consider the discrete amounts of data, say 26 letters in the alphabet as an example, or say our 10 decimal digits 0 to 9. Then larger quantities can be built from discrete values, like say words, say computer, that C, again I can, this is a letter, O is a letter, M is a letter. So each can be these letters, these are some discrete non-numerical letters. Then the 10 decimal numbers, if I take a huge number, say 9563210, then each one, each decimal digit, this is a discrete number. Again, that computers operate on binary values 0 and 1. Now, why this binary are used? Because it is easy to represent electrically. Already in the introductory classes we have discussed this part. Mainly say voltage and current. Say if it is a power supply which is generating 5 volt supply, then say 0 to 2 we have just marked that as a 0, and say 2 to 5 we are marked that as a 1. So these voltages and currents we can easily represent by 0 and 1. Now this can be implemented using circuits and create the building blocks of modern computers. So this is the main basics of the computer systems. So before starting the number system, as the real world is more conversant with the decimal number system, so quickly we go through that thing, and then what is the similarity of developing the number system or the binary number system, we will see that thing. All of we know that these decimal numbers are made of 10 digits. Normally the concept comes from our that 10 fingers of our hand, and that is why it is restricted to 10 numbers. And then these are some notation, say 0 to 9. Now this number of items that decimal number represent, say one decimal number is 8653. So normally this gives the positional value, that means all of we know this is the unit, 3 is the place of the unit, 5 is placed in 10th position, 6 is placed in 100th position, and 8 is placed in 1000. So 8 into 10 to the power 3 means 1000 plus 6 into 10 square, 5 into 10 to the power 1 and 3 into 10 to the power 0. So this 8653, this is the number of items. Actually the decimal number represents by 8653. Now if it is a fraction, then how we can actually quantify this thing? Similarly that 97654, so the position of 9 is, if we start from here, that 0, 1, 2, 3, 4, then 9 is the 4th position. So 9 into 10 to the power 4, then 7 into 10 to the power 3, 6 into 10 square, 5 into 10 to the power 1, 4 into 10 to the power 0. Now this should be minus 1, because already I have reached 0th position. So this is minus 1, that means position of 3 is minus 1. So this is 3 into 10 to the power minus 1. So this should be the 3 into 10 to the power minus 1, then 5 into 10 to the power minus 2, and in formal notation we can write that 97654.35 when the number system is 10. Now, this 10 we define this as a base or radix. So, one thing from here, it is from our common concept of decimal number system, that every number system has one base. Here the base is 10. That means that in decimal number 10 base means 10 distinct digits 0 to 9 are used to represent a number system. So, if we see now the octal numbers. So, for the octal numbers the base is 8. So, for this octal number system, that 0 to 7, these 8 digits are used in the system to represent a number. So, the number of items that an octal number represent, it should be, the base is 8 and the positions are same. So, if it is 4, 5, 3, 6, then this is 0th position, because this is there is no fraction here, this is 0th position, this is 3 is in first position means 1, 5 is in second position 2 and the 4 is in position 3 place value. So, 4 into it should be 4 into 8 to the power 3 because base is 8, 5 into 8 square, 3 into 8 to the power 1, 6 into 8 to the power 0, and if I do this thing, if I do this computation, if I multiply this and then we do this addition, I will be getting 1362 in our decimal system. So, 4536 in octal system is nothing but the 1362, that means 1362 in our normal decimal system. Now, how do we compute the fractions? So, fractions say 465 and then 0.27 in when the base is 8. So, that integer portion again that will be 4 into 8 square plus 6 into 8 to the power 1, 5 into 8 to the power 0, then it should be place value should be decremented, that means 2 into 8 to the power minus 1, 7 into 8 to the power minus 2, and if we compute this thing, then we will get the decimal equivalent of the 465.27 in base 8. Now, one thing you notice that these octal numbers do not use digits 8 or 9. So, only 0 to 7 these 8 numbers are used, that is why the base is 8. Now, similarly, I have hexadecimal numbers. Hexadecimal numbers are made of 16 digits. So, this should be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then 10, 11, 12, 13, 14, 15. So, 0 to 15, these will be of the 16 numbers. Now, see that as already that, okay, if I take that thing, say if it is 16 numbers I take, so hexadecimal, the base is base is 16. So, there should be 16 distinct numbers, say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. Now, from 0 to 9 these are all distinct. So, I will keep as it is. Now, see here 10 means again this is a repetition, that means again the 1 and 0 these two values are used. So, this is represented as A, that means A means in hex or hexadecimal number system it is 10. Similarly, this is B means 11, C means 12, D means 13, E means 14 and F means our 15. So, 0 to 9 and then A, B, C, D, E, F, these are the 16 distinct numbers that are used in our hexadecimal numbers. So, now number of items that an hex number represent, this is similar, only here the base is 16. So, I am taking one number A29. So, our A means actually it is in decimal system it is 10. So, this is 10 into 16 square, because the place value of A is 2. If I start from here it will be 0, 1, 2. So, 10 into 16 square plus 2 into 16 to the power 1, 9 into 16 to the power 0, and if I do this multiplication and addition, then I will be getting 2601 in our decimal number systems. And the fraction can be treated as the same way that we have handled the octal and the decimal. Say if the number is 2b5.27, it should be in 16. So, the base should be in hexadecimal, the base should be 16. Then it will be the place value of 2 is 2, that means it should be 2 into 16 square. Then the place value of B is 1, so it will be 11 into 16 to the power 1. Then 5 into 16 to the power 0, and now after the decimal point that place value is minus 1. So, this is 2 into 16 to the power minus 1, and 7 means this is 7 into 16 to the power minus 2. So, if we do this computation, we will be getting the number in the decimal number systems. Now, we will take our binary number systems, because already several times I mentioned that in digital design that we will be mainly using the binary numbers, and in the introduction also I mentioned that the mainly binary numbers are used for computer application and particularly for the digital cases. So, binary numbers are made of binary digits, means 2 only 0 and 1, that means here the base is 2. So, here our binary number systems, our base is 2. So, number of items that a binary number represent, as the digits are only 2, 1, 0, 1, 1 in base 2, it will be 1 into 2 to the power 3, 0 into 2 square, 1 into 2 to the power 1 plus 1 into 2 to the power 0, and if we compute this thing, say 2 to the power 3 is 8, this is 0 multiplied by 2 square means 0. So, this will be 2, 8 2 plus 2 10. So, this will be my numbers, that 8 plus 2 plus 1, that means my 11 in decimal number systems. Now, how I get the binary fractions? Again in the similar way, that 1 into 2 square, here 1 into 2 to the power 1, 0 into 2 to the power 0, plus after decimal point it is 1 into 2 to the power minus 1, means this is equal to half 1 by 2, this is equal to, it is multiplied by 0, so it is of no meaning, it is 0. So, this will be giving my decimal number. Now, these groups of 8 bits are called a byte. In binary number systems, the 8 bits are called a byte, and groups of 4 bits it is called a nibble. So, if we generalize now that our number systems, see that how we can, first thing, for any number system, say for any number system, I need a base, say that R is the base or called radix. So, say I have one number in any that number system whose base is A0, A1, base is R, say A2, A3, A4 and so on, and after decimal it has some A minus 1, A minus 2, etc. Then the number of radix R can be written as say I am representing this by NR, and this should be, say if we start from A4, that means the position is here, the position is 0, it is 1 already, 2, 3, 4. So, it should be A4 into R to the power 4 plus A3 into R to the power 3 plus A2 into R to the power 2 plus A1 into R to the power 1 plus A0 into R to the power 0. This is my integer portion. Now, what will be my the fraction after decimal point? So, it will be A minus 1 R to the power minus 1, because the place value is now minus 1, then plus A to the power A minus 2 R to the power minus 2. So, this is my general representation of a number system, and so far we have discussed that for binary number systems, that radix is 2, for octal that radix is 8, for hexadecimal radix is 16, and our known decimal, that is our real world, works in when the radix is 10. So, normally these are the 4 different number systems that are mainly used in digital design. Now, another thing is, already we have noticed that mainly the binary are very suitable for that digital design. So, that means even the number is in the octal number system or hexadecimal number system or in decimal number system, if somehow I can convert that thing to our binary number system, then obviously it will be very efficient and advantageous for the implementation of digital logic. So, now we see that how this conversion between 2 number systems we can do. See, so what we have seen, that we have 4 such number systems. Okay. Our main concentrate where we concentrate, or what is that main thing we want, that is our binary number system, where the radix is 2. Now, the most common one that our digital world or our real world works, that is our decimal number system, where the radix is 10. Just now we have read another 2, one is called our octal number system, where the base is 8 and the hexadecimal where base is 16. So, conversion means I can do decimal to binary, that means given a decimal number, I can convert it to binary, and the vice versa. That means, if a binary number is given, then its decimal is also possible. Now, say octal, if it is the similar thing will happen, that binary to octal it is possible and octal to binary is possible. Similarly, the binary to hexadecimal is possible, hexadecimal to binary is possible, and again we will see that actually conversion between decimal to octal or decimal to hexadecimal, that is also possible. But here our main emphasis is on the binary systems, and that is why we are more interested to be converted the 3 decimal systems to the binary, or from binary to other 3. But now we will see that actually how this can be converted. So, first thing is that we are thinking that conversion from decimal to any other base. See, first what we will do, that this is a general principle or general rule I can tell, that divide the decimal number by the base. That means, base means here the number systems that I want to convert from decimal number systems. Say if I want decimal to binary, that means my base is 2. So, the remainder is the lowest order digit, and repeat the first two steps until no divisor remains. So, this is the general rule of our, better you can tell, this is the my general rule of conversion from decimal to any other number systems. Only the base will be changed. First we take one example, one very simple example. Say I have decimal value 13. So, say this is my 13, when the base is 10, I want to convert that thing. So, first I will divide my, I want to convert from decimal to, I want to convert decimal to binary, okay, decimal to binary. So, my binary means base is 2. So, 13 divided by 2. So, the integer portion, that means my quotient I get, this is actually my quotient, I get 6 and remainder is 1. So, if I write the remainder again, my remainder should be, here my remainder should be 1. And see that I am writing this remainder as if the coefficient, say 0 equal to 1. Now, already I got that my quotient becomes 6. So, next step I am taking the 6 and I will repeat the division. So, this will be 6 divided by 2. So, quotient is 3, remainder is 0. So, again this 0 I am taking that the coefficient should be A1 is 0. Now, that quotient becomes 3. So, again 3 divided by 2 in the next step. So, this becomes quotient becomes 1 and now the remainder becomes 1. So, this is my next coefficient is 1. Now, that quotient is, or that number becomes 1. So, again 1 divided by 2, now my quotient becomes 0 because 1 is less than 2. So, my remainder is 1 and I stop because my it will stop when the quotient becomes 0. So, this is my last coefficient, that is 1, and I will be taking this coefficient because this is my A3. So, in reverse order, that means A3, A2, A1 is 0. This is my A3, A2, A1 is 0. So, this is 1, 1, 0, 1, 1, 1, 0, 1. So, now if you want to check so far the what we have done. So, what I get? I get that my binary representation of 13, binary representation of that 13 in decimal system, I got 1, 1, 0, 1. So, if I see that what is that 1, 1, 0, 1 in decimal, if I want to check, then see this is my 0th position, this is my first 1 position, 2 and 3, this is in base 2. So, what will be the thing? This 1 into this is 2 to the power 3 because place value is 3, then 1 coefficient is 1 into 2 to the power 2, then plus 0 into 1 to 2 to the power 2 to the power 1, 2 to the power 1 plus 1 into 2 to the power 0. So, what will be the value? Then it is becomes 8, then 4, this is 0 multiplied by 2, then this is 1 into 2 to the power 0 means 1. So, this becomes 13 in 10, 10 decimal digit. So, it is verifying the result. Now, decimal fraction to another base. Okay. So, just now what we have seen, that how the, if it is a decimal integer number, then how it is changed to the any other base. Now, if it is fraction, that means after decimal point, then instead of division we will be doing multiplication. So, what will be the general rule? The general rule is that multiply decimal number by the base. Again I am considering that this is for, say, for decimal to any other number system, say binary, then this is for 2. So, we will be multiply. The integer is the highest order digit. So, the integer I will get, I will keep that thing. Now, here it is the highest order digit, that means the reverse one, and repeat the first 2 steps until fraction becomes 0. So, this is my general rule of converting the decimal fractions to any other number systems, or either it can be binary, octal or hexadecimal. See one example first. So, now I am taking that 0.625. This is in our decimal number systems. So, what was the rule? That rule is that multiplied, it should be multiplied by the base. So, here we are taking that this to binary, this to binary means 2. So, 0.625 into 2, what we will be getting? We will be getting, if we multiply this thing, we will be getting 1.25. See, this integer is 1 and the current fraction value is 0.25. So, this is the coefficient is, now this is the highest, that is why that a minus 1, that minus 1th coefficient minus the position value is minus 1th and the coefficient value is 1. This is the integer I got. Now, I take the current fraction, that means 0.25. So, 0.250, again I will multiply by 2. So, it will be 0.50. So, integer is 0, current fraction is 0.5. So, my a minus 2 means the second position coefficient is 0. Now, again 0.50 into 2, because I have to continue until I get my fraction to be 0. So, here it is 0.50, again now if I multiply I get a integer 1 and now my fraction becomes 0. So, the coefficient is 1. Now, I will take in this order, that 1 0 1, not in the reverse order, that when we have taken that we have converted the decimal integer to binary, we have taken the reverse order. Now, we are taking that the correct order, that 1 0 1. So, 0.625 means that 0 is that actually before decimal, this is 0, then a minus 1, a minus 2, a minus 3, and these are nothing but 101. So, this is 0.1012 in base 2. So, this is my conversion. So, now we we do one example. Okay. Say we are taking now one decimal value. First we see the some decimal value, some decimal number. Some decimal number, say 7, 8, 9, 10. Or say 78 when the base is 10. So, first how will I want that this to be some it should be converted by some value in in binary number system, and I want to know what is my value of x. So, what was the general rule? Because this is pure integer value. So, I will divide by 2, because in binary system the base is 2. So, I will divide that thing by 2. What will be the value? That this is 39. My remainder is 0. So, I am keeping the remainder, say this is my remainder. Now, this is my quotient, again I am dividing by 2. So, this is 19, again my remainder is 1, again I am dividing by 2, 9, 18, remainder is 1, again I am dividing by 2, remainder is 1, again I am dividing by 2, remainder is 0, I am dividing by 2, remainder is 0, I am dividing by 2. Now, my quotient becomes 0 and this remainder is 1. Now, what I will be doing, as it is a integer, I will be taking in reverse. My x is 1 0 0 1 1 1 0. So, it means that 78 in decimal number system is same as that of, or it is converted to 100 111 0 in binary number system. So, this is if I do in this decimal. Now, if I take one say fraction, say I am taking some decimal fraction. Now, I am taking some decimal fraction. So, I am taking 0.75, and I want that some binary value. Now, what is the rule? Now, here the rule is the multiplication by the base. Here the base value is 2. So, what I will be doing? 0.75 into 2. What will be the thing? So, 1.5 0.50. So, my integer is 1 and fraction is 0.50. So, 0.50 again into 2. So, this will be, I know that this will be 1.00. So, this becomes again the 1, integer value is 1, and we will stop because my fraction becomes 0. Now, I will take in normal direction, that means first I got 1, then I got 1. So, it will be in this direction. So, 0.75 10 will be 1 1. That means that this should be 0 means 0. So, this should be 0.112. This is 0.112. So, we have seen that how the decimal number, the binary, that can be converted. See, now I am taking, say if I want decimal to octal, because we have, when we have given the general rule that my base can be anything, because from decimal number system to any other conversion binary or any other number system I can convert. If I want, so now we see that how we can convert the decimal number system to octal. Now, decimal number system means the base is 10 and octal means the base is 8. So, if I take an example, say 961, then in decimal number system, what it will be in octal means base is 8. So, what was our general rule? That was the division by base. So, again I am taking that number 961, I am dividing that thing by my base 8. So, it will be 120 the quotient and the remainder is 1. Again I am taking the division I am doing. So, quotient is 15, remainder is 0. Again division, now the remainder is 7. Again I do the division, so quotient becomes 0, it will be 1. And now if I take in reverse direction, so 9 6 1 in decimal value, it will be 1701 in octal system. And the similar way I can do the fraction also. Let us take one example. So, if it is the, say some decimal, we take that 0.35, and then what we will be doing? Again I want some x in octal. So, now rule is multiplication. So, 0.35, again I will be this will be multiplied by 8, and what will be the value? This will be 2.80. So, my integer becomes 2. Now, this decimal is, again it will be multiplied by 8. So, this will be 6.40. Then again this will be 40 into 8, this becomes 3.20, and it will be so on. Say again, if I take 0.60 and then it will be see again that 0.80 has come back. So, that means from here it will be a repetition. So, now if I take in the same direction, it will be 26 means 0.26 314, and again it should come that 6314 should be repeated. So, this is my that 0.35 in our 10 decimal system. So, in that way, that from decimal system to any other number systems I can easily convert. Now, again if we come back to the binary and the our decimal system, because our main emphasis is the binary, that means how we can convert the numbers from any other number system to binary number systems. So, if I consider that the number should be say in this way, just if I form a table, if it takes n, and what would be the value of 2 to the power n, means say if my value is 0, then it will be some 2 to the power 0. If my value is 1, then it should be 2 to the power 1. If it is 2, then it will be 2 square. If it is say 10, then it will be 2 to the power 10. Now, say if it is 20, say if my n value is, that means if my n value is 20, then it should be 2 to the power 20. If it is 40 or say, then it will be 2 to the power 40. Like that, it will be growing, the binary numbers will be growing. Now, another is the binary coded decimal code. It is called that BCD. That BCD is used for applications where it is interfacing between a digital device and a human being. Say the digital voltmeter, and the BCD uses each binary bits to represent each decimal. Say that if we take one example, this is a 854 in decimal number system, then each decimal number is represented as a 4-bit binary numbers. That means 8 means it is a 100. Just now the way we have converted, if I convert that thing to 8, then it will be 1000. The 5 means it will be 0101, and then 4 means it is a 0100. So, this will be the BCD code. Now, one thing is this BCD is very inefficient. Why? Say if I take this example 999, then 10 bits are needed if I convert it into, or I represent into a binary number system, but 12 bits are needed if I convert it into a BCD number system. See that 2 bits are extra, and if the number increases, then it is actually it becomes 20 to 24. So, this is not, BCD is not always efficient. So, binary is very efficient in that sense. Now, we stop here and I give some small questions, that quiz, that very simple questions, that why, mainly based on this today's discussion, that why binary number system is used for most digital systems, and then some of the conversions, and this is just for practice, that convert the following binary numbers to decimals, because here already they are in base 2 and I have to do the reverse one. Again here it is a binary to decimal, and convert the following decimal numbers to binary, that this 3, and convert the following decimal and binary numbers to BCD. So, I will stop today's class, and these again digital number systems will be continued in the next class. Before starting the today's lecture, first we quickly go through the last day's lectures answers of the quiz. The first question was, why binary number system is used for most digital system. Now, as we know, the most of the digital systems use discrete number of parameter levels, say the voltage levels or current levels, and the finite number of values in a digital system can be represented by a vector of signals with just 2 values. That is the binary signals, means that 2 that can be represented by a string of 0 and 1, 0 0 1 0, or 10 that is 1 0 1 0, and the device which processes this signal is very simple to implement, say a switch, either 0 or 1 means switch on or switch off, or open or closed. So, that is why that mainly binary number system is used for most of the digital systems. Second question was the conversion, the following binary numbers to decimal. So, as here the binary is in binary radix is 2. So, using the formula we did, this should be 10101 means 1 into 2 to the power 4, 4 is the place value. Similarly, 0 into 2 to the power 3 plus 1 into 2 square, 0 into 2 to the power 1, 1 into 2 to the power 0, and the non-integer part 0 into 2 to the power minus 1, 0 into 2 to the power minus 2, 1 into 2 to the